Okay, so we're starting chapter 6 here, and the whole idea is we're going to transform non-homogeneous boundary conditions to homogeneous boundary conditions. Okay, so they say, well, what we'd like to do is solve the general problem, u sub t minus alpha squared u sub xx. Now, this is a non-homogeneous problem here to begin with, let alone the boundary conditions. But says we would like to be able to solve this, where then in the most general sense, we have some alpha 1 u sub x at 0 and t plus beta 1 u of 0 and t is equal to some g1 of t. Now, so this is the non-homogeneous boundary condition. Non-homogeneous boundary condition. And so if this was, if g1 of t was a 0, that would be homogeneous. And similarly, we have alpha 2 u sub x. Now they use an L, I'm just going to use a 1 plus beta 2 u1 of t g2 of t. And then an initial condition, u of x and 0 is some phi of x. Okay, so we would like to be able to solve this problem. What they say is, well, we may not be able to, that the way we can solve this problem is actually transform it and they use an uppercase u, so we'll do an uppercase u like that, where that particular u satisfies u sub t minus alpha squared u sub xx, so that part's nice. Now, notice this is a different function. This was a lowercase f of x and t. This is uppercase. Does not mean it's the antiderivative. It just means it's a different function. Now here things look similar. We still have the alpha 1 u sub x 0t plus beta 1 u of 0t. But now it's equal to 0, so now we have the homogeneous boundary conditions. And then an alpha 2 u sub x, and again I'm just going to use a 1 as opposed to an L. Beta 2 u1 t equals 0. And now our u sub x and 0, our initial condition, is well, they've got this messed up. They have a phi of x, which is incorrect. Let's see. I don't know. They're using the uppercase u, so I don't know. I'll just do a psi of x. Okay, so see, this is not the same as phi of x. Okay, up here. So, I don't have a note in my book that they screwed that up. So that must be the first time I've noticed it, I suppose. But they will see right away that that the new initial condition is definitely not the old initial condition. Okay, so that's the idea. And now notice this whole thing here, this form, whether or not we've got it equal to 0 or some function of t. Again, remember that the most general sense here, if we actually use all of that, because there's nothing that says we can't have either alpha or beta be 0 in either of these cases. But this most general case was the idea that we had a rod that was insulated, okay, but the ends here were in a bath, and here was also in a bath. Okay, that was I think boundary conditions 2 in whatever lesson that was, maybe lesson 4 or something like that. But this was the case. But if we change things up here, we can do whatever we want. We can have now if we only deal with u, so if you just have u of like 0 and t equals 0, actually we call those Dirichlet boundary conditions, something like that. And so u of 1 of t equals 0. These are Dirichlet boundary conditions. So that would be the case where we, just have those pieces, the betas. But of course, once we just have beta times that, divide both sides by beta, beta doesn't need to be there. And then similarly, if it's the derivatives that are 0, u sub x 0t equals 0, u sub x 1t is equal to 0. We call these Neumann boundary conditions. Okay, so we can have these mixed ones here. That would be the bath again. And then we can either have the Dirichlet boundary conditions or the Neumann boundary conditions, or some mix thereof, right? We could have, and actually in this lesson, that's what they do, is they, at the 0 side, they do a Dirichlet boundary condition, and then at the right-hand side, they do the bath later on in this chapter or this lesson. Okay, so we're looking at that. Now, I guess the simplest place to start would be that we have something like, for our boundary conditions, we just have like u of 0t is equal to, what letter do they use? I gotta find the letter here they use. K1 and K2, so K1 and then UT K2. So we've seen that before, and what we know is that eventually, if this is, say K1, and up there's K2, say. Here's 0, here's 1. Then this would be our solution as t goes to infinity. We would expect just a straight line, something like that. And so, since that's a straight line, here's the basic idea they suggest is they say, well, let's just get the equation of that line. Okay, and well, in this case, if you use their L, if this is an L, then the slope is equal to K2 minus K1 over L. If we just use 1, it just makes that K2 minus K1. With a y-intercept of K1, so y-intercept equals K1, actually 0 K1, but so this particular function right here is simply K2 minus K1 times x plus K1. And so actually what they suggest then is that if we say, okay, our solution, so this is the small u, the original problem, we say our u of xt is just equal to, and they write it in this order, K1 plus x times K2 minus K1. Now again, they have a divided by L. I'm not worrying about that. And then plus the uppercase U of x and t. Well, then what we know for this is that if we take, U equal little u minus the K1 plus x, K2 minus K1, then we see that u of 0 and t equals u of 1 and t, and they all equal 0. Okay, because this was the left and right hand side of u. That was the non-zero part. If we subtract that from u, we get the 0 part. And so this is our transform function. We're looking for this function. And now what happens here? We'll notice that u sub t is actually equal to u sub t, little u sub t, okay, because that has no t in it, so the derivative with respect to t is 0. And then it's linear, so if we look at u sub xx, that's equal to the second derivative with respect to x of u. Okay, because again, second derivative of a linear function is 0. And so we end up here with that same u sub t minus alpha squared u sub xx. And actually, if that was whatever the right-hand side was, we get the same thing. So, way back here, if the right-hand side was this lowercase f of x and t, it actually still is in this case because we didn't change anything here. Okay, and if this happens to be, equal to 0, then we already know how to solve this problem. Okay, so if it's not 0, we don't know how to solve it, but I mean, you and I, right, because we haven't gotten far enough in the lessons, but we, as long as that's homogeneous, then under these conditions, we do know how to solve this problem. And the only difference then is, we would have our, oops, make that u sub t minus alpha squared u sub xx equals 0. We have our, in this case, Dirichlet boundary conditions. We've got our u of 0 and t equals 0, u of 1 and t equals 0. But now our initial condition, and you see this is where things have changed, is that u of x and 0 now becomes the old phi of x minus k1 plus x times k2 minus k1. And so that is our transform problem. So what happens is simply we get a new initial condition like this. Okay, and again, remember, where did that come from? Just right here. Okay, just this stuff here, because u, big uppercase U is lowercase u minus this function, the k1, the linear function. And so, well, if little u of x and 0 was phi of x, so we can put an x there, then uppercase U, which is equal to little u minus our linear function here. I'm just going to call that L of x for the moment. All right, so that's just L of x up here. Well, then that would have to be for u of x and 0, that would have to be phi of x minus L of x. And so there we go. That's all we have to do to solve the new problem. And then, once we get our solution, so we'll get our solution u of x and t, and from the homogeneous boundary conditions, and then our actual solution, original, right, is just well, let me write that as a small u, is just our small u of x and t, but that's just equal to u of x and t, the solution from our homogeneous boundary conditions, plus, looks like, okay, plus our L of x, or k1 plus x times k2 minus k1. So pretty straightforward, and we can do a sage example with something like that, but there you go. That's the solution. So if we can already solve this one, we just go ahead and solve that one for that initial condition, and then once we have it, then we add this back in, and we have our solution. Okay, So that is sort of the simplest situation we could have. Other than that, it can get much more complicated. So let's stop this one here and start a new video.